Hello to all. Welcome back to my another video which is on nanotube field effect transistor. Now, in my previous video we have discussed about nanowire field effect transistor. In this video I will discuss about basic silicon nanotube field effect transistor, its device physics, device simulation. I will discuss about the code as well, and I will discuss about how to create 2D and 3D structure. So let just find out what is silicon nanotube field effect transistor. Basically, silicon nanotube field effect transistor is basically a transistor which is created by silicon nanotube. Now, as we know, nanotube is basically hollow inside. So what we have done, we have kept another gate, which is an inner gate inside the nanotube, which controls or which gives the extra control over the channel electrostatics and increase the conductivity of the current. This helps basically to control the channel electrostatics. So we have a lot of benefits using silicon nanotube FET. So in the figure, you can see that how we place silicon nanotube and inner gate inside the nanotube. There are two gates. One is outer gate, which is outside the nanotube, and one is inner gate, which is inside the nanotube. So we have also used spacers so that minimize the fringing effects, and we have also used different contacts so that we can easily create the inner gate and outer gate contacts. Now move to the fabrication. Now I would like to show you that how it would be difficult or how it would be easier to create the nanotube structure. So here is the nanotube structure which is being fabricated. Now we can see nanotube inside the channel. The nanotube channel is inside and out. There is an outer gate. Then there is another a inner gate. So that inner gate is basically a tabular topology. The silicon nanotube exhibits best device structure which is expected to have the exceptional charge control which allows the further scaling of the device. So why we are moving to the nanotube? Now what's the question is that why we are moving to the nanotube? Now we have in previous video I have discussed about nanowire. Now nanowires are facing problems when they are being scaled down. The problem is higher number of short channel effects are coming, very high leakage current is coming, okay, and very high drain induced barrier lowering is coming, gate induced drain leakage is coming. So number of factors that are being degraded in the nanowire are being upgraded in the nanotube, and you can easily scale down the device. So we will calibrate this device with the use of another silicon nanowire, and using same kind of models we simulate the nanotube FET. Now let's come to device physics. Now here in this video I have simulate the junctionless FET because nanotube is similar to the nanowire junction nanowire, okay, but in this video I have simulated the nanotube junctionless FETs. So in junctionless FETs, first of all I would like to discuss about uniform doping. Means the channel is uniformly doped whether it is p-type or n-type. No abrupt junctions are there. simplifying device behavior. Now, nanotube itself is a very complex structure. So if we delicately use it, we can easily get the very good results. So next, the problem is threshold voltage. Now we have to, you know, keep the gate work function in such a way that we will get the device turned off and we will device the turn off on, because threshold voltage is very important factor while you are designing a device. So we have to select the gate work function very delicately, diameter and doping level to uh, optimize the threshold voltage. Next is gate controlled conductivity. Now above threshold voltage, an accumulation or inversion layer forms for the current flow. Gate voltage modulates the thickness of the conductive layer. However, gate control conductivity increases. Why? Because we have used two gates, inner gate and outer gate. Now, absence of junctionless leads to the uniform carrier distribution along the channel. Depleting these carriers is key to junctionless field effect transistor operation. Carrier control in achieved by modulating the conductive layer formed near the nanotube surface. Now, the conductivity will be increased with the use of inner gate. Next is short channel effects. Now we know that different type of short channel effects are there. So basically DIBL, subthreshold swing, gate induced barrier lowering, leakage currents, and higher electric field, and basically drain source to drain direct tunneling, lateral band to band tunneling. These are the various effects that comes when you scale down the device. So by using nanotube field effect transistor, these devices, short channel effects of the such nanowires and MOSFETs will be reduced. So you can use the short channel devices with the very good performance of DIBL and subthreshold swing. Now we know that subthreshold swing has ideal value of 60 millivolt per decade at room temperature. So using nanotube junctionless FET, this value reaches to 60 to 61 millivolt per decade, which is almost similar to the ideal. Now another factor is switching speed or switching efficiency, which is measured by the on current ratio to the off current ratio. So in this nanotube junctionless FET, the on current to the off current ratio is approximately 10 raised to power 12 to 12 raised to power 13, varies accordingly. Now, if we scale down the device to the 7 nanometer or below the 10 nanometer, your switching efficiency is also maintained at 10 raised to power 8 or 9, which is a very good as compared to the silicon nanowire devices. So, with the use of gate control method, the superior gate control has been provided, which reaches the subthreshold swing and the ion by IF ratio up to the mark and minimizes the influence of the drains on the channel barrier. This also reduces the leakage current, which is mainly due to the lateral band-to-band tunneling. Now, carrier transport mechanism. Now, this nanotube is basically used for the short channel devices. So, short channel lengths, electron can be moved from source to drain with the ballistic transport method. Ballistic means there is very high mobility, very no resistance is there. So, that is basically approximately ballistic transport. Diffusive transport, which is basically dominant at the room temperature, and it is basically a practical device. In the practical devices, these kind of methods are used. Now, contact resistance between the nanotube and the metal electrode is significant. Impact of overall device performance is very good. So, role of contacts, we can easily change the metals and we can easily change the work functions of the electrode so that we can reduce the resistance between the source and the drain metal contacts. Now, junctionless nanotube devices, the performance is basically depend upon the length of the channel length and the environment also. So ballistic transport sometimes offers very high, very good speeds, but it is very crucial to minimize the resistance between the source and the drain. So according to the usage of the nanotube, in the particular applications, we have to optimize the performance with the help of excellent work function, using the channel engineering, using the contact engineering, and using the device engineering. So all these combines, and then we can create the very good nanotube junctionless FETs for the further applications. Now we will discuss about how we can simulate the device. So using Atlas, Silvaco Atlas, we can easily simulate the device. It is the Silvaco Atlas is basically a simulator that evaluates the behavior of the semiconductor device and other physical parameters. It also evaluates the device characteristics, which is electrical characteristics, conduction mechanism, and charge distribution. It provides a diverse set of physical models like Fermi direct statistics, advanced mobility models. It has also fully integrated capabilities like another runtime environment on which we can easily visualize the results that are being extracted from the atlas, that is on the tonic plot. You can easily write and create the code for the particular device environment on the deck build. The another process simulators are Athena and Supreme. It uses very powerful and sophisticated numerical techniques to solve and making the initial strategies. So device simulation is very important, and to visualize the device virtually before fabrication, we have to simulate it on the device simulator. Now, Atlas has three basic structures. First of all, physical structure, the model to be used, the bias condition of the device. So Atlas device simulation does the simulation. On the DevEdit, use structure, and mesh editor, you create the structure and produces the mesh. Now Anthena also does the same, which is a simulation for process simulation. Now, when the structure file is created along with the command file that goes to the Atlas device simulator, and there it a runtime output is created, that output can be seen on the Tony plot for the further visualization. Next is Atlas programming. Now you have to learn how you can easily program. So first of all, we will start with command Go Atlas. We use the Atlas simulator, so we will go for the Go Atlas command. Now there you have to specify whether you are using 2D simulator or 3D simulator along with the multiple factor for the mesh. The element in the input desk can be categorized in 5 groups. So these 5 groups are created structure files, solve files, meshing, region, electrodes, and doping. So in meshing, you evaluate the equations and at every node, okay, you create the dense mesh and there is a higher number of nodes. You created the coarse mesh, you created the less number of nodes. but accuracy is very degraded. So you have to plan accordingly, whether you need the optimize the time and accuracy. The material models need to be defined. Now you have to define the materials as well. Now materials you need to define, its property you need to define. If you're using silicon material, then you have to define all the properties of the silicon material. Basically, it includes all the properties when you define the material. But if there are another extra properties you want to add, that you can add. Now next is models you need to add. Basic models are basically like mobility models, band gap narrowing models, like other electric field dependent models, temperature models. So all the models you need to specify. Contacts you need to specify which, like source, drain, gate contacts as well. Also you need to specify the interface charges. The numerical model that are used in the solving the equations are very helpful and you need to be specified. These solutions are to be specified specifically. The statements used for the solution specific are log, solve, load, and save. Now finally, you can extract the result on the Tony plot and you can visualize the results. Now, Atlas simulations of nanotube junctionless FET. Here you have decided the mesh structure, radial meshing, angular meshing, and z-axis meshing. So you can easily see that you have the different structure and different meshing. Next, you have to define the regions with the materials. So here I am defining the region with the material and then I am defining the electrode definition. So I have already given the name, source, drain and gate 1. So gate and gate 1 are basically the inner and the outer gate. So when you are defining for the two gates, you have to provide the gates, each gate contacts. Next is region, your doping. Now here I am using doping like structure. So I am using the doping of 6 raised to power 6 into 1 is to power 18 in the silicon region, or I am using N-type uniform doping. So material models we are using here are CVT model, CMOB model, CSC MOB, SRH model, Auger model, Fermi model, band gap narrowing model, and BT band to band tunneling non-local model. So whenever you are considering for the GIDL or lateral band to band tunneling, you have to consider the tunneling models as well. Further, you created the contact definition now where you have to give the particular work function to the gate. Next is you are giving the material model specification. You have defined that silicon and silicon dioxide has the traps. Those are defined by this structure. Now next is numerical modeling. Numerical modeling is a very important step that you have to be specified and you have to use in Newton Raphson method or another methods in which are easily available. Now output is the another command where you have to specify whether what kind of another parameters that you want in the structure. So here I have valence band, conduction band, charges, E lines, H lines. So all the parameters I have put it here. So it will come when you take the output on the Tony plot. Now the solution specification. Now you have to ramp up the gate voltage and specify the drain voltage. So both are on both the parameters you have to give the particular values. Now Tony plot, you can easily get the Tony plot and 3D Tony plot. So that structure will be created on the Tony plot and you can easily visualize. Now you can extract the threshold voltage by using this method, extract the ion current, I of current, and ion by I of ratio. So all these are being executed with the help of Atlas. Now, this is the structure that we have created using the 3D structure of nanotube junctionless FET, and this is the 2D structure of nanotube junctionless FET. Now, you can visualize the IDVD characteristics. So this is all about nanotube field effect transistor. This is the one type of nanotube field effect junctionless field effect transistor I have explained here. You can create and you can visualize different structures of nanotube junctionless FET. I hope this finds you well and you will get the knowledge you want from this video. We will make another videos on different structures in the coming videos. So please stay tuned and mention in the comments that what kind of another videos you would like to have or what kind of another structures you want to know about. So we will create the another videos according to that. Thank you. Thank you so much. Have a nice day. Good night.